Welcome back. In this video, you will learn about sequences and how to determine their convergence. Let's get to it. Alright, so a sequence in mathematics is an ordered list of terms or values. And so here I have an example of an nth term of a sequence. And so what do I mean by an nth term? Well, this expression here, a sub n is equal to 2 to the power of n, represents the terms of a sequence that are determined based on the value of n. Now you can sort of view a sequence as a function where instead of plugging in values of x, we are plugging in values of n, except for sequences, n is typically only going to be positive integers starting at 1. And so if we let n equal 1, we would have our first term of our sequence, which is a sub 1, and that will be equal to 2 to the power of 1. And so that would be equal to 2. Then our second term, if we let n equal 2, that would be the next positive integer. We would have a sub 2 is equal to 2 squared, and 2 squared is equal to 4. Then we could have a third term. If we let n equal 3, that would be the next positive integer. And so we have a sub 3 is equal to 2 cubed, which is equal to 8. And so we could continue to create more terms. We could have a sub 4, a sub 5, and so on, and we would continue to build this list of terms. And so while this expression represents the nth term of a sequence, we represent the entire sequence with braces around a sub n. And that will be equal to 2 to the power of n, surrounded with braces, and that will be equal to our list of terms. And so if we start with a sub 1, we have 2, so we'll have 2, comma, a sub 2, and a sub 2 is 4, so our next term is 4, and then a sub 3 is 8, and so we'll have 8 as our next term, and then this would continue on forever for a sub 4, a sub 5, and so on. Alright, and so this is a basic example of a sequence in mathematics, and unless it's stated otherwise, a sequence, a sub n, is assumed to start at n equals 1, like we have right here. Our first term was a sub 1, and it will continue on forever towards infinity. Alright, so unless you were told otherwise, that's what you can assume about sequences. Let's take a look at a few more examples of some sequences. So here we have an entire sequence, a sub n, which is equal to 2 times n. And so if we write out the list of terms, this is what we'll have. We're going to have our brace there. And then a sub 1 is going to be when n is equal to 1. So if n is equal to 1, we'll have 2 times 1. Then our next term, a sub 2, is going to be 2 times 2. Then our next term, a sub 3, will be 2 times 3. Our next term, a sub 4, will be 2 times 4, and so on. All right? And so we would say that this is equal to the following list of terms of 2 times 1, which is 2, and then 2 times 2, which is 4, and then 2 times 3, which is 6, and then 2 times 4, which is 8, and so on. And so what we find here is that this sequence, 2 times n, is equal to an ordered list of terms that are the positive even integers, right? We have 2, then 4, then 6, then 8, and this is going to continue on forever with the rest of our positive even integers. Now here's another example. We have the sequence a sub n is equal to negative 1 to the power of n. And so now what's going to happen with this sequence? What will our terms look like? Well, this is going to be equal to our first term, a sub 1, where we will have negative 1 to the first power, and then we will have a sub 2, where we'll have negative 1 to the second power, then we'll have a sub 3, where we have negative 1 to the third power, and then a sub 4, where we have negative 1 to the fourth power, and so on. And so now if we simplify these terms, this will be equal to negative 1 to the first power. That's just going to be negative 1. So we'll have negative 1, comma, negative 1 squared. So we have positive 1. Then our next term, a sub 3, we have negative 1 cubed, and negative 1 times itself 3 times will be negative 1. So we have negative 1 again. And then our next term, we have negative 1 to the fourth power. Now negative 1 times itself 4 times is going to be positive 1. And so we have positive 1 again, and then this will continue on from there. Now what do you notice about these terms for our sequence? Well, whenever we had an odd power, our term was negative 1, but whenever we had an even power, our term is positive 1. And so we can see that for the entirety of this sequence, we're just going to be oscillating back and forth between -1 and +1. And so those two numbers are going to be the only values that appear in this sequence. We just go back and forth between each value for each term. All right, so this is going to be an important sequence going forward. You're going to see -1 to the power of n a lot as we go further down the road in calculus and we use sequences for other concepts. All right, now if the starting value of n or the ending value of n are going to be different for a sequence, sometimes you will see this notation used. You'll have braces around your nth term, but then you'll have a lower and upper bound. The lower bound will tell you what n is starting at, and the upper bound will tell you what the highest value of n will be. Now in this case, we're going to be starting at n equals 0 instead of the usual assumed value of n equals 1, and we're going to increase towards infinity. That's the same as what we've been doing before. Our terms are never going to end. And so in this case, if n is starting at 0, our terms will look like this. We'll have a sub 0, and then 0 divided by 0 plus 1. Then we'll have a sub 1, so we'll have 1 divided by 1 plus 1. Then a sub 2, which will be 2 divided by 2 plus 1. And then a sub 3, which will be 3 divided by 3 plus 1, and so on. All right, and so if we simplify those terms, we have 0 divided by 0 plus 1. That's just 0 divided by 1, so our first term is 0. Then we have 1 divided by 1 plus 1, so that's 1 divided by 2, so we have 1/2. Then our next term, we have 2 divided by 2 plus 1, that's 2 divided by 3, or 2/3. And then we have 3 divided by 3 plus 1, which is 3 divided by 4, or 3/4. And then that would continue on forever. All right, and so these would be the terms for this sequence. So just be aware that sometimes you may see this notation where you have a lower and upper bound, and typically that will be used to let you know if a starting value of n or an ending value of n is different than what we typically assume. And so here's another example of that notation for a sequence. In this case, we have 3 times n divided by n plus 2 as our nth term, and it starts at n equals 2 and ends at n equals 5. All right, so in this case, this sequence has a set number of terms. It does not go on forever. And so we can actually write all of those terms out. And so this would be equal to our first term of a sub 2, since we're starting with n equals 2, and we'll plug 2 into this expression here. So we have 3 times 2 divided by 2 plus 2. Then our next term will be a sub 3, and we'll have 3 times 3 divided by 3 plus 2. Then our next term will be a sub 4, and we'll have 3 times 4 divided by 4 plus 2. And then our last term will be a sub 5, since this sequence ends at n equals 5. We're not going to have an a sub 6 or an a sub 7 and so on. The sequence is going to end with this term. So we will have 3 times 5 divided by 5 plus 2. And that is the end of the sequence. And so if we simplify, this will be equal to 3 times 2, which is 6, divided by 4. And so we would have 6/4. But that reduces to 3/2. So I'm just going to rewrite that. And we will have 3/2. And then our next term, we'll have 3 times 3, which is 9, divided by 3 plus 2, which is 5. So we have 9/5. That will be our next term. And then our third term will be 3 times 4 divided by 4 plus 2. And so we have 12 divided by 6, which is just equal to 2. So we have 2. And then our final term is 3 times 5 divided by 5 plus 2. So we have 15 divided by 7. And so 15/7 is the final term of our sequence. And so these are the terms for this sequence. All right, so just be aware of that notation. It's not very common, but it can be useful to know if you're given a sequence that starts at a different value of n and ends at a different value of n as well. But if you don't see this notation, you could always assume that a sequence starts at n equals 1 and it will go on forever towards infinity. You will have an infinite number of terms. Now, sometimes you might encounter a sequence that is defined recursively. And what that means is that the sequence is defined in such a way that the next term of the sequence is going to depend on the previous term. And so if you take a look at this example here, we have the sequence a sub n, where the first term, a sub 1, is equal to 10, And then the term a sub n plus 1 is equal to a sub n minus 2. And so what does this mean? Well, what this is telling us is that the next term in the sequence, a sub n plus 1, the next term after a sub n, will be the previous term, a sub n minus 2. So let's write out the terms here. Let's see what this would look like. Our first term, we are told, is equal to 10, right? A sub 1 is equal to 10, and so a sub 1 is 10. But then what would a sub 2 be? Well, the next term, a sub n plus 1, will be equal to the previous term minus 2. And so if a sub n is a sub 1, then a sub n plus 1 will be a sub 2. And so we can find a sub 2 by taking a sub 1 and subtracting 2. That's what this equation right here is telling us. We can take the previous term, subtract 2 to get the next term. So a sub 2 will be equal to 10 minus 2. And 10 minus 2 is equal to 8. So I'll rewrite that, and we'll have 8. And then what about our next term, a sub 3? Well, we will take our previous term and subtract 2 again. And so we'll have 8 minus 2, and that's equal to 6. And so we could rewrite that as 6. And so we could continue on from there. We could continue to take our previous term, subtract 2, to get our next term. And that would continue on forever. And so this is an example of a recursively defined sequence. They're not very commonly used in calculus problems, but it can be helpful to at least see it one time so that you know what they are if you come across them. Just know that with a recursively defined sequence, you have to be provided with at least the first term of the sequence, and then you also have to be told how to find the remaining terms with some kind of equation like we have right here. Okay, and so to finalize our list of terms, we have 10, 8, 6, and we would continue to subtract 2, so we could have 4, 2, 0, and so on. All right, and so this is the list of terms for our sequence a sub n, which is recursively defined. All right, now similar to how we can find a list of terms for a sequence based on an nth term, we can also reverse this process and find the nth term of a sequence a sub n to represent a list of terms by recognizing a pattern. And so these types of problems can be a little bit trickier than just writing out the terms of a sequence, because recognizing a pattern involves a little bit of intuition, and there's not always a set way to do it every single time. However, there is a process that you can use to make pattern recognition a little bit easier, and I want to show that to you here. So we're given this list of terms for a sequence. We have 4, and then 5 divided by the square root of 2, and then 6 divided by the square root of 3, and 7 divided by 2. And so in order to recognize a pattern here and express that with an nth term, what we should first do is just write out what each term is equal to. And so this is what I mean. We know that a sub 1 is going to be equal to 4, a sub 2 is going to be equal to 5 divided by the square root of 2, a sub 3 is equal to 6 divided by the square root of 3, and a sub 4 is equal to 7 divided by 2. Now what you want to do is look at all of your terms here and see if you can notice anything that they all have in common, or something that most of them have in common. And so if you look at these 4 terms here, you can see that 3 of them are rational numbers. We have 5 divided by the square root of 2, we have 6 divided by the square root of 3, and 7 divided by 2. And so let's rewrite a sub 1 to also be a rational expression. 4 could be rewritten to be 4 divided by 1, right? So we could have that a sub 1 is 4 divided by 1. And now that more closely matches how the rest of our terms look. But now notice that 2 of our terms also include a square root in the denominator. We have the square root of 2, then the square root of 3, but then our other terms have 1 and 2. But we can actually rewrite 1 to be the square root of 1, right? The square root of 1 is just 1. And so rewriting this to be the square root of 1 is totally legal because this is still equal to 4. But then what about this denominator of 2? Well, 2 is the square root of 4. So we can rewrite that to be the square root of 4. And now all of our terms are very similar. We have rational expressions with an integer in the numerator and a square root in the denominator. And so now that they all look very similar, what we want to do is compare them to the value of n for that term. So for our first term, n is equal to 1, and so do you see any 1s within this expression? Well, in the denominator, we have the square root of 1. Now if we look at our next term, n is equal to 2, in the denominator, we have the square root of 2. Then for our third term, where n is equal to 3, this is equal to a fraction where we have the square root of 3 in the denominator. And then when n is equal to 4, we have the square root of 4. And so we can conclude that the denominator for each of our terms will be the square root of whatever value n is. So we can start to express our nth term by saying that the denominator will be the square root of n. But now what about the numerator? Well, let's see if we can rewrite each of these numerators to incorporate the value of n for each of those terms. So for example, this will be equal to the square root of 1 in a denominator, but how could we rewrite 4 so that we have 1 within that expression? Well, 4 is equal to 1 plus 3, so that's one way that we could write it. And so let's see if we can develop some type of pattern with the rest of our terms by breaking up the numerators in a similar way. So for a sub 2, 5 would be equal to 2 plus 3, right? So that would incorporate our value of n, which is 2. So we have 2 plus 3 divided by the square root of 2. Then for our next term, 6 would be equal to 3 plus 3, right? That would incorporate our value of n. So we have 3 plus 3 divided by the square root of 3. And then what about our last term here? How can we incorporate 4 into the numerator? Well, 7 would be equal to 4 plus 3. So we have 4 plus 3 divided by the square root of 4. Now look at all of our numerators here. All of them are the value of n plus 3. So we have 1 plus 3, 2 plus 3, 3 plus 3, and 4 plus 3. And so we can conclude for this sequence that the numerator will always be the value of n plus 3. And so if we go to our nth term here, we'll have n plus 3 in the numerator. And so our sequence, a sub n, will be equal to n plus 3 divided by the square root of n. That is the sequence that will represent this list of terms. All right, now here's another example where we have a list of terms where we want to recognize a pattern and write out the nth term for that sequence. And so let's do the same thing we did last time. Let's start by just writing out all of our terms and seeing what they have in common with relation to the value of n. So we know that a sub 1 is equal to negative 1, a sub 2 is equal to 1/2, a sub 3 is equal to negative 1/6, a sub 4 is equal to 1/24, and a sub 5 is equal to negative 1 divided by 120. All right, now in this case, I see that all of our terms, except for the first one, are rational expressions or fractions, and so we could rewrite negative 1 to be negative 1 divided by 1, and that's going to match the rest of our terms a little bit better. But now what kind of pattern do we see in the numerator and the denominator? Well, in this case, I'm going to look at the numerators first. Notice that we have negative 1, then positive 1, then negative 1, then positive 1, then negative 1. This is actually a very common pattern that you will see with sequences. In fact, we've already looked at this sequence earlier in this lesson. When you are alternating between negative 1 and positive 1, that is most likely going to be represented with negative 1 to the power of n, right? Since we start with negative 1, and we're alternating between positive 1 and negative 1, then this will represent that numerator. When n is equal to 1, negative 1 to the first power is negative 1, and then negative 1 squared is positive 1 for n equals 2, and then for n equals 3, negative 1 cubed is negative 1, and so on. And so our nth term, a sub n, will at least be equal to negative 1 to the power of n in the numerator. But what about the denominator? What's going on with these denominators? Well, we have 1, then 2, then 6, then 24, then 120. So these are increasingly getting larger, but let's see if we can somehow incorporate the value of n into those denominators to see if we can find some sort of pattern. Now, this first denominator is just 1, so if n is equal to 1, the denominator is 1. For the next term, when n is equal to 2, the denominator is also 2. And so it looks like the denominator is just going to be the value of n until we look at our third term. When n is equal to 3, we have 6. And then it starts to get really big. When n is equal to 4, we have 24. And when n is equal to 5, we have 120. And so if you want to pause the video before I tell you what is happening with these denominators, see if you can recognize the pattern yourself first. But if you just want to know what it is, I'm going to tell you it right now. What's happening is the next denominator is a result of multiplying the value of n by the previous denominator, right? So for n equals 1, we just have 1, but then next we have 2, which is equal to n equals 2 times 1. 1 times 2 is 2. Then for our next denominator, we have 6, which is equal to 3, our value of n, times 2. And then 24 is equal to 4 times 6, and 120 is equal to 5 times 24. And we can actually represent this by using a factorial. And so here's what I mean by that. This is equal to negative 1 divided by 1. This is equal to positive 1 divided by 1 times 2. This is equal to negative 1 divided by 1 times 2 times 3. This is equal to positive 1 divided by 1 times 2 times 3 times 4. And this is equal to negative 1 divided by 1 times 2 times 3 times 4 times 5. Right? We take the previous denominator and multiply it by the next value of n. And so we continue that pattern forever with the rest of our terms. And so each of these denominators is just the value of n factorial. And if you don't remember, we represent that with an exclamation point. So for this denominator, that is equal to 5 factorial. And all that means is that we are multiplying all the integers from 1 to 5 together. So we have 1 times 2 times 3 times 4 times 5. The only exception to that rule is that 0 factorial is equal to 1. So just keep that in mind. But in general, we can represent the denominators with n factorial. So we'll have n factorial. All right, and so that might seem like a difficult pattern to recognize the first time around, but now that you are aware that factorials are going to show up within sequences, they should be easier to spot when you're trying to recognize a pattern, especially if you see a sequence that includes 1, then 2, then 6, then 24, then 120, because each of those are just 1 factorial, 2 factorial, 3 factorial, and so on. And so if you ever have a sequence of those numbers or something similar to that, you probably are working with a factorial. All right, but in this case, our sequence a sub n is equal to negative 1 to the power of n divided by n factorial. That is the sequence that represents this list of terms. All right, and so now that we have established what sequences are, we can finally begin to analyze them by using calculus. Specifically, we want to focus on determining if the terms of a sequence approach some limiting value or if they converge to a specific value. And so for example, I want you to consider this sequence right here. We have a sub n is equal to 1 divided by 2 to the power of n. If we were to write out those terms, this would be equal to 1 divided by 2 to the power of 1. Then our next term would be 1 divided by 2 to the power of 2. Then we'd have 1 divided by 2 to the power of 3. And then 1 divided by 2 to the power of 4, and so on. And that would be equal to 1/2, 1/4, 1/8, 1/16, and so on. And what's happening here with the terms in this sequence is each term is getting smaller, right? 1/2 in decimal form is 0.5, 1/4 is 0.25, 1/8 is 0.125, and 1/16 is 0.0625. And so as we continue to add more terms to this sequence, their decimal value is getting smaller and smaller towards 0. And so it would seem that the terms in this sequence are headed towards the value of 0. And we can further confirm this by graphing the terms of our sequence, where our horizontal axis are the values of n, and the vertical axis is a sub n. So when n is equal to 1, our first term a sub 1 is 1/2. And then when n is equal to 2, we have 1/4. And when n is equal to 3, we have 1/8, and so on. And you can see, as our values of n get larger towards infinity, the terms of our sequence are getting closer to 0. And so while we can see this visually from a graph, and also from the decimal values of our terms, we can actually show this convergence of a sequence by using a limit and treating the sequence like a function. Specifically, we're going to look at a limit of a sequence as that value of n approaches infinity. And so here's how this is going to work. If we have a sequence, a sub n, we can take the limit as n approaches infinity of the nth term of the sequence, And if it is equal to some limit L, meaning that L exists, then the sequence converges to that value of L. If L does not exist, and that includes infinity or negative infinity as the result of the limit, then the sequence does not converge to a value, it diverges. And so by taking the limit as n approaches infinity for a sequence, we can determine whether it converges to one specific value or if it's never going to converge to any value. And so that can mean that the terms just get bigger forever and they're not headed anywhere except infinity, or they could just be oscillating between two values or multiple values and never settles on one specific value. And so let's take a look at some examples of determining the convergence of sequences by using a limit. Okay, so here's our first example. We have the sequence a sub n is equal to 5 minus 3 divided by n. And so if we want to determine the convergence of this sequence, what we can do is take the limit as n approaches infinity of a sub n. Now a sub n is equal to 5 minus 3 divided by n, and so let's rewrite that. We will have 5 minus 3 divided by n. Now the limit as n approaches infinity of a constant will just be that constant, so this is equal to 5 minus the limit as n approaches infinity of 3 divided by n. Now remember, when you have a limit of a value approaching infinity of a fixed value divided by that value, which is approaching infinity, that's going to be equal to 0. We have a fixed value of 3 divided by n, which is increasing towards infinity, and as that denominator gets larger, the value of that fraction gets smaller towards 0. And so we would say that 3 divided by n, where n is approaching infinity, would be equal to 0. And so this is equal to 5. And so since this limit exists, it's equal to 5, we can conclude that the terms of this sequence will converge to 5. Each subsequent term of this sequence is going to get closer and closer to the value of 5. Okay, and so we would say that this converges to 5. All right, let's take a look at another example. Here we have the sequence a sub n is equal to 7n plus 1. And so if we want to determine the convergence of this sequence, what we can do is take the limit as n approaches infinity for that sequence. And so we'll have the limit as n approaches infinity of 7n plus 1. Now in this case, if n is approaching infinity for 7n, then n is going to continually get larger and larger, right? So as n gets larger and larger, and we're multiplying it by 7, it's still getting larger and larger, and then we're adding 1 to it, and so it's still getting larger, and so this whole expression, as n approaches infinity, is just going to continue to approach infinity. It's just going to get bigger and bigger. And so this limit is equal to infinity, but that is not a specific value, and so we can't say that this limit converges to any specific value. When we have a limit of a sequence that is equal to infinity or negative infinity, we have to say that this sequence diverges. And that means that the terms of the sequence are not approaching some specific value. In this case, since the limit was approaching infinity, we would say that the terms of the sequence are forever getting larger, and they're not converging to any specific value. All right, so in this case, this sequence diverges. Next up, we have this sequence, a sub n is equal to 9 times n divided by 3n minus 2. Now, if we want to determine if this sequence converges, we can take the limit of that sequence as n approaches infinity. So we'll have the limit as n approaches infinity of 9n divided by 3n minus 2. Now, if we look at this expression as n approaches infinity, in the numerator, we have 9 times n, and so if n is increasingly getting larger, we just have that increasing value times 9, so that whole numerator is going to increase. So in the numerator, we have infinity, but what about the denominator? As n approaches infinity, we have 3 times n, and n is increasingly getting larger, and so if we multiply it by 3, it's still getting larger, and then we're subtracting 2, but if this is continually getting larger, subtracting 2 isn't really going to do anything, and so this whole denominator is still an increasing value that will be approaching infinity. And so in the denominator, we have infinity. And so this limit is in an indeterminate form. We have infinity divided by infinity. And so if you recall from a previous lesson, if we have an indeterminate form, like infinity divided by infinity, we can use L'Hopital's rule to help us evaluate this limit. And so since this is an indeterminate form that is compatible with L'Hopital's rule, what we can do is simplify our limit by taking the derivative of the numerator and the denominator. And so that is what L'Hopital's rule allows us to do. So if we do that, we'll have that this is equal to the limit as n approaches infinity of the derivative of 9n. And so in this case, we're going to be taking a derivative with respect to n, since everything is in terms of n. And so the derivative of a variable to the first power, like we have right here, n, is just going to be equal to its coefficient. So the derivative will be 9. And in the denominator, we have the same thing happening. We have 3 times n to the first power. So the derivative of that will be 3, and the derivative of -2, which is a constant, will be 0. So we have 9 divided by 3. Now 9 divided by 3 is equal to 3, so this is equal to the limit as n approaches infinity of 3, and the limit as n approaches anything of a constant is just equal to that constant. And so this is equal to 3, which means that our sequence is going to converge to 3. We would say that it converges to 3, right? And so what that means is that the terms of our sequence, each subsequent term is getting closer and closer to the value of 3. All right, so here's our next sequence. We have a sub n is equal to 1 plus -1 to the power of n. And so if we want to determine the convergence of the sequence to see if it converges or diverges, we need to take the limit as n approaches infinity for this sequence. So we'll have the limit as n approaches infinity of 1 plus -1 to the power of n. Now in this case, we're actually not going to be able to solve this limit. The limit as n approaches infinity of 1 is just 1, but the limit as n approaches infinity for -1 to the power of n is going to give us an issue. And that's because -1 to the power of n, as n gets larger, this is only going to produce 2 different results. If -1 is raised to an odd power, it's going to be -1, but if -1 is raised to an even power, then it's going to be +1. And so if we were to look at the terms of this sequence real quick, what we'll have is that a sub 1 will be 1 plus -1, right? -1 to the first power is -1. Then a sub 2 will be 1 plus 1, because -1 squared is +1. And then we're going to alternate between those two values. A sub 3 will be 1 plus -1, and a sub 4 will be 1 plus 1, and so on. And that is because -1 cubed would be -1, and -1 to the fourth power would be +1. And so what we have here is that this is equal to 0, 2, 0, 2, and so on, right? 1 plus -1 is 0, and 1 plus 1 is 2, and we're going to alternate between those two values of 0 and 2. And so because this sequence oscillates between those two values, it's not converging to one specific value. It's either 0 or 2, 0 or 2. It's not getting closer to any specific value. And so although we can't evaluate this limit, it's just going to be undefined, we can still conclude that this sequence is not going to converge. It's never going to get closer to one specific value, and so in this case, we would say that this sequence diverges. And that would be our solution if we were asked to determine the convergence of this sequence. Let's look at one more example for this video. All right, so here's our last example. We have the sequence a sub n is equal to -1 to the power of n divided by n. And so if we want to determine the convergence of this sequence, what we can do is take the limit as n approaches infinity for that sequence. So we'll have the limit as n approaches infinity of -1 to the power of n divided by n. Now, if you just went through the last example with me, you know that we can't take the limit of -1 to the power of n. But now just because you see that in our limit doesn't necessarily mean the sequence is going to diverge. In this case, we have a rational expression, and so the result might be a little bit different. Now, we still can't evaluate the limit for -1 to the power of n as n approaches infinity, because this is going to oscillate between -1 and +1, but we do know that that numerator is always going to be a fixed value. It's either going to be -1 or +1. And then in the denominator, as n approaches infinity, n is going to get larger and larger, and so we would say that it approaches infinity, and so what we have here is a fixed value divided by an infinite value. And we know that when we see that, it's equal to 0. That rational expression is going to get closer and closer to 0 as n approaches infinity. And so we could conclude that this is equal to 0, but since we can't actually take the limit of this numerator, we actually have to show a little bit more work to prove that this limit is equal to 0. Okay, so even though we can look at this logically and say it's going to be equal to 0, that's what this is going to converge to, we need a different way to show that a limit like this that we can't really evaluate does converge. And so this is where we make use of something known as the squeeze theorem for sequences. And the squeeze theorem for sequences says this: if we have three sequences, a sub n, b sub n, and c sub n, where c sub n is greater than or equal to b sub n, and b sub n is greater than or equal to a sub n, then if we have the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of c sub n, and they're both equal to some limit L, then we can conclude that the limit as n approaches infinity of b sub n is also equal to L. So here's what this is saying. If we have three sequences where the terms of b sub n are greater than or equal to a sub n, but less than or equal to c sub n, meaning that it is between these two sequences, and these two sequences both have the same limit, then that middle sequence must also have that same limit, right? If the terms of that sequence lie between the terms of the other two sequences, and these both converge to the same value, then that sequence must also converge to that same value. And so if we go back to our example, I just want to show you briefly how that looks visually. If we were to graph three sequences, let's say that this represents our first sequence, a sub n, and that is converging to 0. And then let's say that this is our third sequence, c sub n, and that is also converging to 0. b sub n would have to be in between those two sequences. And so it has no choice but to also converge to 0, right? So b sub n has to have the same limit as a sub n and c sub n if it lies in between them. And so what the squeeze theorem allows us to do is if we can find two sequences that this sequence lies between, and those two other sequences have the same limit, then this sequence will also have that limit. And so if we set up the squeeze theorem here, we're going to have a sub n less than or equal to b sub n less than or equal to c sub n, and we're going to let b sub n be our sequence of -1 to the power of n divided by n. Now, what two sequences can we pick that this sequence would lie between? Well, remember, the numerator here is going to oscillate between -1 and +1. And so we could say that this sequence is always going to be greater than or equal to -1 divided by n, and it will always be less than or equal to +1 divided by n. It's never going to be greater than 1 divided by n, because that numerator is always going to be either -1 or 1, which also means that it's never going to be less than -1 divided by n. And so, if we take the limit as n approaches infinity of both of these sequences, watch what happens. The limit as n approaches infinity of -1 divided by n is just going to be equal to 0, because we have -1 divided by n, and as n approaches infinity, this denominator gets increasingly larger, and so a fixed value divided by an increasing denominator is just going to be equal to 0. And we'll find the same thing for the limit as n approaches infinity of +1 divided by n. We have a fixed value of 1 divided by an increasing denominator, right? N is approaching infinity, and so 1 divided by infinity is equal to 0. And so if the limit as n approaches infinity of -1 divided by n is equal to 0, then we would say that 0 is less than or equal to the limit as n approaches infinity of -1 to the power of n divided by n, which is less than or equal to the limit of 1 divided by n, which we found is 0. And so since the limit of this sequence has to be between 0 and 0, it has no choice but to also be 0. And so we can conclude that that sequence converges to 0, right? The limit of that sequence will be 0 thanks to the squeeze theorem. We know that it's always going to be between these two sequences, and so since they both have a limit of 0, meaning their terms both converge to 0, then the terms of this sequence will also converge to 0. All right, so you might come across some sequences where if you want to determine their convergence, you're not going to be able to show the evaluation of the limit as n approaches infinity like you would with some other sequences. And so what you can do is use the squeeze theorem for sequences to get around that and still show that your sequence converges to some value. This is especially going to be helpful when you have sequences that involve factorials, because evaluating the limit as n approaches infinity for some sequences with factorials are not possible to evaluate without the use of the squeeze theorem. And so this is it for this video, but if you want to see more examples, including sequences that have factorials, feel free to check out my examples video that'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.